Okay, then I will continue with the optional material, which is using optimization in Python. So basically here, today I will only introduce the SciPy library. As some of you may know, for other solvers such as Ruby and maybe other solvers, they also have a Python API. So basically you can use Python to call other solvers, but today I will only introduce the so-called the simplest one, which is the SciPy library. So for the SciPy library and MATLAB, they all use the matrix vector form for optimization modeling, which is different from GAMS. GAMS use the algebraic form, which means you will define sets and then all the decision variables, all the equations will be indexed on those sets. But for matrix vector form, all the decision variables must be put in one vector, which means you only have one set of index, which is the position. So for example, in the previous example, as Lanyu has introduced, for the decision variable, we have two sets of indices. One is for the origin, the other is for the destination. But if you want to program those in MATLAB or use SciPy library, then you must put everything in a vector. Which means actually vector matrix form is not as powerful as algebraic form when you deal with like large-scale problems. Because as you can imagine, when the scale of the problem or the dimensionality of the problem becomes very large, then managing one single set of index, which is the position of the elements in the vector, will be more difficult. But if you can define more sets to index over, then the algebraic form will be better. Yeah. So yes. So basically, I will use Python to resolve the previous optimization problem, which has been introduced by Lanyu. Here is that the slide is reproduced here. So basically here, like this formulation is more suitable for the algebraic form because you already have indices and you already index all the variables over those sets. But for vector form, as I have mentioned previously, you don't have those I and j two sets of indices, you only have one. So we need to change it to matrix vector form. So all the decision variables must now put in one single vector. So here we have to kind of you can think of it as linearize the originally we have two sets of indices, then is like a matrix, and then you need to linearize it to a vector. So for the position because we are using Python, then for Python usually for those programming language, index starts from 0. So I use the convention start from x0 to x5. So yeah, in MATLAB it will be x1 to x6, but it's just a minor difference. So here we have like six decision variables, which represents the amount of transportation from Seattle to New York to Chicago to Topeka, and then from San Diego to New York, Chicago, and Topeka. And also we have the set of, and we also have the corresponding cost for each transportation. So the objective function is like we need to sum up all the costs. So here in the matrix and vector form, if we put every cost like in the same order as the decision variable, which means C0 corresponding to the transportation cost from Seattle to New York, then in this way our objective function will just be the inner product of the C vector and the X vector. And then for the bounds, yeah, they are all transportation quantities, so they must be non-negative. And then the more trickier thing is for the two inequality constraints. For the first one, we need to sum up over the index of I, which is the index over the origins. So here, if we put everything in a vector, then we must selectively sum up everything shipping from Seattle and then everything shipping from San Diego. So we have this kind of matrix here. So if you multiply the matrix A with the vector X, then you will have a two elements vector. So the first element will correspond to everything shipping from Seattle, while the second element will correspond to everything shipped from San Diego. So in that sense, if you use the matrix A multiplied by the vector X, then it must be smaller or equal to the availability of those like cans, as in the first constraint. Now it's translated into a matrix and vector form. Similarly, for the second one, you need to sum up over all the destinations, which means for these two, we will sum up over this one and this one. So there are ones here, and all the other like elements in the same row will be 0. So in that sense, if you multiply these two, then you will get everything like reaching New York, Chicago, and Topeka as here. So we will have the matrix vector like formulation like this. Basically, this kind of formulation is also useful for MATLAB. If you use like F-incon, then you will have the inequality constraint matrix and equality constraint matrix, which follows the same like formulation here. So later I will show you like do a demo to code in Python. So yeah, you already know nowadays we don't have excellent tutors as Lanyu, then we need to Google it. So basically we need to Google like how to use those things, right? So yeah, as mentioned, I will use SciPy and then optimize. Then we can search for a tutorial for a quick one. Yeah, see here. Take some time. Yeah, there are the table of contents. So you have different solving methods, and then you can solve different kinds of problems. Today I will show you the simplest one, which is like this one, the sequential least square quadratic programming algorithm, which is relatively easier to use. Then you can see the official demo here. So how to solve our problem? Well, for those who have used Python before, then we have different editors and platforms to run the code. Since today I will do a presentation, then I will run it on Jupyter Notebook. You can also choose other editors and other like platforms to run your Python code. But if you are new to Python, then maybe you can. I would recommend you to use MATLAB instead. Otherwise, it will take you some efforts to learn how to use Python first. But then, yeah, it will be kind of the learning curve will not be very smooth. So yeah, let's create a new notebook in Python 3. Then how to do these things? First of all, as mentioned previously, also mentioned by Jiali, the solvers are already written by the community. So we need to import the library first. How to import the library? Well, actually this tutorial is written in sequence. So actually the import statement is written in the very beginning. In the very beginning of it, like here. Yeah. Yeah, you can see these two lines. Because for SciPy, it also calls functions from NumPy, which is a numerical computation library built in Python. So we need to import both of them. Yeah, okay. As NumPy, first of all, we need to import NumPy, and then we need to this style means import everything. So in Jupyter Notebook, if you shift enter, then it will basically run the code. Yeah. So this is for the purpose of presentation. If you use other like platforms to run Python, then how to run the code will be different. Okay, then let's see how to translate our formulation into Python. So here we need an objective function. Okay, where is it? It takes so long. Objective function is here. So in this statement, then it calls the minimize it minimizes this objective function, which is this one. For this one, for the Rosen function is defined previously in this tutorial because they are written in sequence. So in this subsection, it is not defined again. For us, we need to define our own objective function. So basically, if you know Python before, then it's just a Python function. Yeah. Objective function will yeah. So Python will like indicate the blocking of the codes by indentation. Yeah. So yeah. We also need to define our cost vector, which is this C. for how to define an array, you can use np.array and then put in a list. So it will give you an array of that size with all the elements there. So if you refer to the problem formulation, it will correspond to the cost of different it will correspond to the cost of different shipping routes. Yeah. So 1.8 and then 1.4. So after the unlike MATLAB, you don't need to have the semicolon at the end of each line. So for this one, since it's easy, we will just do a dot product. We will do a dot product between the decision variable, which is x, and the cost vector, which is defined here. All the numbers are taken from the hands-on example from the previous section. Then the next thing, let's see how to do this. Then the next thing we need to do, the x0 is the initial guess or the initial point of the solver. So for this problem, since it's not very difficult, we will use a relatively naive initial guess. For more complicated problems, as mentioned by Jiali, you may need to use a more carefully guessed initial point. The methods, this is the name for this solver, and then here is the Jacobian. So as will be introduced by Prof. later in the module, so a lot of solving algorithms are derivative based. You need the derivative of the function with respect to the decision variables. So if the function outputs a scalar, then this kind of derivative will be called gradient. But then if the function outputs a vector, then you can see the output is a vector, input is a vector, then the derivative will be a matrix, which is called the Jacobian. But it's not written clearly in this documentation. Actually, this Jacobian is optional. If you provide it, then Python will use it. If you don't provide it, Python will use it will calculate it numerically. So here for simplicity, we'll omit this Jacobian. Now comes to the constraints, equality and inequality constraints. Basically, they're all defined in terms of Python lambda functions, as seen there. Again, the Jacobians are optional. Although it's provided in this documentation and not explicitly said optional is optional. So if we don't want to define, then we can just ignore the third part. All right. Okay. Then we need to construct the matrix for the two inequality constraints first, and then construct the constraints. So okay, for the matrix A will be np.a array. For two-dimensional arrays, basically in Python is a list of lists. Because list, you can put any object in the list. So a list is also an object. You will have So that's it. As some of you may know, you have other ways to construct matrices. Because when the dimensionality is higher, when for example we have 1,000 origins, thousands of destinations, then hardcode every element in the matrix will be very tedious. But now, since it's a very simple problem, we will just hardcode everything. So it's like this. Yeah. So this is the vectors and matrix for the first inequality constraint. For the second inequality constraint, similarly. I think it's correct. 325 So now we have defined the matrix and the corresponding vectors for the two inequality constraints. Then we need to follow the syntax of the solver to define those constraints. We need to make sure that remember to check the problem formulation. As can be seen here, the inequality constraints are defined in terms of greater than or equal to 0. Some of the solvers may define like reversely, like smaller or equal to 0. But so here, wait, so slow. So we will define the inequality constraint 1. This curly braces indicates a dictionary in the Python data types. So type is the key, and then is INEQ. And then it's the function, I think. The function will be smaller. Wait, I think it should be this one. I think that's it. Because we need to define everything in a kind of larger than or equal to 0, so we will move the matrix vector product to the right hand side. So it's like the vector A minus the product of matrix A and decision variable X. Yeah. Then okay. So we have defined the two inequality constraints. In this problem, we don't have any inequality constraints. Like here, we have defined the inequality constraints. For equality constraints, this problem don't have. For these options, as mentioned by Jiali, there are some options for the solver. This F tolerance is like for two consecutive execution or iteration of the problem. If the objective function value is differed by less than this amount, then the solver will terminate. This display means whether you want the solver to have some like output during the execution, as can be seen here at the bottom. These are the executions. So for the options, yeah, we will just use this one here. Let's just copy and paste. Yeah. Yeah, just copy and paste here. For the very last one, the bounds is for the bounds of each decision variable. Again, it's defined previously, so it's not defined here, because like this official tutorial is written in sequence. So for things defined in the previous sections, they won't do it again. So it may cause some confusion or difficulty when you first read this kind of thing. You need to refer back, as here. Yes, here. This line of code is how you define the bounds. So let's do this. The bounds. So basically, it took two inputs. The first one is for the lower bounds. The second one is for the upper bounds. Yeah, lower bounds are all 0. Yeah, upper bounds, there is no upper bound, so there is a special value or special constant for Python, which is the num means infinity. Yeah. Here I use hardcode again. Actually, you can have smarter ways to define those things. For example, you can use numpy infinity times a vector of ones, which it will have the same effect, but will save your effort in typing. So eventually, let's come here. Here. Like how you would like to call the functions is like this. Yeah, we will just copy and paste, and then delete unnecessary things. Do some modification here. Yeah. So basically, the first one, as I mentioned previously, is the objective function. So we have defined that the x0 here, we will just use a very naive one, which is all zeros. Yeah, this x0 doesn't really doesn't really like satisfy the constraints. The reason why this can be solved is because like later, as you will know, this is a linear programming problem, which is rather easy to solve. So yeah, so with a very arbitrary initial guess, the solver can still handle it. For the Jacobian, it's optional, so we are lazy, we won't need it. So, yeah. And then for the constraints, is in a list of equality and inequality constraints. So here we only have inequality constraints, but we have two. So in 1, in 2. For the options, we will use the one provided in the tutorial, and for the bounds, we have defined it previously here, right? Yeah. Yeah. And then for the result, it will store a lot of things. If you want to see the optimal solution to the problem, here you will need to print result.x. So basically, let's see. Yeah. Oh, typo. Okay, let's try to run it. It may not. Oh, it works so fast. So yeah, so you can see it works, and then for the print statement, it gives you the solution. Actually, you can check with the solution provided by line using GAMS. It's the same thing. From Seattle to New York 50, and then Seattle to Chicago 300, Seattle to Topeka 0, San Diego to New York 275, and San Diego to Chicago 0, San Diego to Topeka 275. Yeah. The current function value, this is the value of your objective function. Now since it's terminated successfully, this is the optimal value of the objective function. For the iterations means the algorithm runs 20 iterations. As you can see here, the gradient evaluations is 20, but the function evaluation is 160. The reason why there is a difference here is we didn't define the Jacobian. So as you may know, you can also calculate the derivatives numerically. But then if you increase your number of function evaluations. So for larger problems, actually there is a trade-off. That to define the Jacobian, you need to put in more effort, and then you run the risk of like defined wrongly. But then with Jacobian, the solver can solve the problem rather quickly, like at least faster than this one. But if you ignore the Jacobian, then you have an easy life encoding, but then the function may take. There will be more function evaluation, so if the function is very hard to evaluate, then it will take a longer time for the solver to provide a value here. So yeah, that's it. Yeah, I think for those who have used Python before, then it will be kind of easy to understand. But if you haven't heard Python before, then if you don't know like how to define a function in Python, how to define a list, how define a dictionary in Python, then the learning curve is not very friendly, especially if you want to use this directly in the individual project. But having said that, this matrix vector formulation is very important. If you don't use Python, you can also use MATLAB. The same idea like follows. Yeah. For MATLAB, I won't really do a coding, but if we search fmin_con, and then we just go to see the syntax of fmin_con. Like yeah. As you can see here, all those A equality and A are matrix, and X is a vector. So these two basically is the same formulation like in the vector matrix form. So being able to convert the original like mathematical formulation to this matrix vector form will also be helpful when you do coding in MATLAB. Yeah. Okay. Yeah. Thank you.
Thanks for this is the first Python part in this optimization. We use only to teach MATLAB and GAMS. So I got some questions. Say, if I know MATLAB already, I can just use MATLAB. Of course you can, If you want to try to learn more programming, or if you want to use some professional optimization software like games, it's also your options. You can choose based on the problem you want to solve. And also some of the resources, like the way Inan just showed, is perfect how you learn yourself. Now we live in the Google age, so we can always get the tutorial online. So by the way, you learn new knowledge and you can practice yourself. And also for like this, if you just search MATLAB, MathWorks, this website will provide all the information. I will just have help in the MATLAB window. You just help anything. It will give you a lot. Just use the help function. So this is a base learning resources. We just want to quickly know how to code those problems, follow those structures. What's the structure it requires? What's the input? Why you need to learn in the class is about mathematics. What does each of the option mean for you? What is a Jacobi matrix? What is the tolerance? So those things are what we will teach more in the following of the module. But when you implement it, even if you don't know anything about those, you can still implement such problems. But as a talented user, you should be able to know what's default there, what's embedded there. Okay. So also for games, I'll show you the website. So we have because for now we solve the small scale problem. So when the size is within 1,000 or several thousands, you can use the free license to solve it. But if you encounter some infeasible ratio, like if your site is time dependent, you consider every day over 10 years, so it's more than thousands of variables, then this problem can give you an error. When you run the games, you will see license infeasible or those kind of error. Then you can use this website. If you really want to try some real world examples, this is a good example. This news website, we also put it in a reference later. So it's NEOS. This is the website of the online free results. So if once you know how to solve small scale problem, you can always go online to use this server, to upload your server to this, and it will return you the results. It's like cloud computing. You know, this is very valuable because when we do research, sometimes we buy the software license. Can you guess how much is one game's license to buy one server? It seems it's easier to use the server thing, but actually it costs sometimes $10,000 US buy a server on your computer, buy this software to use for a year. So it's really a big business. If you develop your own server, you can even sell it. It's for the powerful servers, but this is an online education platform. You can always upload your programs to this and it return a solution to you. You only need to interpret it. And the results analysis is what we focus most as well. Okay, so hopefully this tutorial session in the first part give you a basic sense how the optimization problem can be programmed, but practice is the most important. When you go back, you can re-practice those examples yourself, especially for Python. I think now these examples you can follow a tutorial online to get allowed. And again, this is a slide though. I want to show you this because I put a poll there. I want to get some of your input to this Slido example. This is just now I got collected your opinion about most of you. Almost everyone has learned MATLAB before who answered my poll there. So 100% MATLAB. And like only one person used GAMS before, but at least 25% have used Python. So it's very good combination. At least you have some programming background. But I also want you to put something here. So W022. Tell us what you like to learn most from this module. Because normally we teach a lot of mathematics. We thought this is good for your learning, for your like scientific background. But also from the journey, like business school, they also teach optimization. They give you a lot of examples. You don't have to understand what's the math behind it, but you know how to implement it. So I want to know what you really want to learn from this module. So some of you have answered already, say programming is the most important, programming and industry applications. So if I got the opinion collected, I will adjust the following content. We can show you more examples, or we can show you more fundamental theories. I'll have another tutorial on Python or on some of the programming language to show you more. So just give me some input here, and we will adjust the content later on to fit you better. Okay, so that concludes the first tutorial session. And in the second part, come back, you can hear more from our guest lecturer, Mr. Clive Chung, about some industry applications and some examples relevant to a module. Okay, so remember to give me some input here as well. Let's have a 10-15 minutes break. We start from 7:45.